Hello, everyone. Today's lecture will go over the first part of the porosity and fluid saturations chapter. Um, this is about a 60-70 slide set, so it's going to be two separate lectures. So that's going to keep us busy for this week. So without further delay, let's start the lecture. First, let's focus the porosity and the pore structures of formations that we produce from oil and gas. Basically, porosity is, by definition, it's a fraction. It's a ratio of two volumes. That's the pore volume of the rock and divided by its bulk volume. So imagine, for example, you would like to measure the porosity of a core plug. Core plug is a disc-shaped sample that we take the core out of the ground and then we take plugs out of it. Imagine this core plug has 1 inch diameter and let's say 2 inch length. Then the bulk volume will be the surface area pi r squared times the length, right? So pi r squared is the area times the length. That's going to give you the bulk volume. That's a quantity that you measure. Pore volume is the space available inside that volume. So this is due to the pore network of the sample. So there are different methods of finding that out, and that's very important for us because it's a indication of the economical consideration, basically. How much pore space we have could be something like equivalent to how large our bucket is, in a sense. Okay, so the larger the pore volume, the larger the porosity is. So this is the ratio of the two volumes, basically. We say VP over VB, pore volume divided by bulk volume. Sometimes we measure pore volume directly, and then we take the ratio to calculate porosity. Sometimes we measure the solid volume, the skeleton of the matrix, VS, the solid volume. If you measure that, then you have to subtract that from the bulk volume to find out the pore volume. Okay, so there are methods that measures the skeleton, the solid volume as well. So both of these ratios could be used fundamentally in the laboratory or using downhole tools. So that's the definition. Basically, you come up with quantities like 0.2, 0.3. Often we report this as a multiplied with 100 as 20%, 30%. We say 30% porosity, meaning that if you have 100 volume of bulk volume 100, out of that 30 is pore and 70 is the skeleton. Okay, the solid. Sometimes we call it solid volume, sometimes we call it grain volume. I kind of like to use the word skeleton when we are talking about the pore networks of these bodies. So these are all same quantity. Okay, so we use phi, the Greek letter phi, as porosity, and that's almost a universal quantity. It's wherever you go in the world, porosity is phi. So which is the nice thing about that. So why we are interested in porosity? My motivational slide is that basically porosity tells me how much fluid is being stored in the reservoir. Actually, it's the most important quantity that we need to perform hydrocarbon in-place calculations, the so-called volumetric calculation. Another important quantity is the permeability. We'll talk about this later on, which indicates fluid transport, right? So again, porosity tells us how much fluid is stored down there in the reservoir, whereas permeability indicates how fast can we produce the stored fluids. Okay, if the permeability is large, the production rates will be larger. So it's a fast depletion, right? If the permeability is low, the production goes down. So in a sense, porosity and permeability are the most fundamental, the quality indicators that we are going to emphasize in our lectures quite a bit. We are going to be experts on porosity discussions and permeability considerations. So these quantities, especially permeability, is being considered as a quality, reservoir quality. And therefore we measure them using different methods to trying to have a better understanding of these methods. This example calculation, I will go through it in the classroom lecture on Tuesday. So let's skip this one and focus to porosity of synthetic materials. Imagine that I have grains that made of billet bowls, like shown here, right? On the left-hand side, imagine that I have the same size billet bowls, and if I line them up like this, the space in between these spheres, these bowls, will be the porosity. Actually, you can do this calculation. You can have a cubic cell attached to it in 3D, and that's going to give you a 47.6% porosity. This is the largest porosity you can get. Okay, 47.6 is pretty high, actually. In geological formations, we almost never, maybe I should say, very rare quantities, such a high value. But this is what happens when you have same size grains and lined up like this. If you change the size of these spheres, you still have 47.6%, by the way. So changing the grain size doesn't change the porosity because they're all the same size. So eventually they go into the same porosity. So 47.6% is the maximum, okay? You can line up these same size spheres in a different way like this. So here, if you notice, basically, they kind of like shifted a little bit, and the first row is kind of filling up the space between the spheres of the second row and the third row, and so on and so forth. So immediately, this is a reduction in porosity because now spheres are taking a large portion of that space available with comparison to the left-hand side. So it drops to 26%, right? Here, again, we have the same size spheres. That's the key quantity. What if you have different size of spheres, like in the bottom one? Well, the porosity could go down even further. It turns out that some of the smaller spheres could easily locate themselves in the pore space of large spheres and leading into a reduction in pore space in this way. So here, the small red spheres kind of like reducing the porosity on the upper left. 47.6% porosity is being reduced because now we have very small spheres as shown in red. Now porosity we record is 14%. Now this is more like the formations that we deal with, okay? We don't have spheres. We don't have same size spheres. We have grains, we have particles, sediments that kind of like get compacted over time. As in the process of burial, there's a sedimentation rate, right? So all these processes of sedimentation followed by diagenesis, leading into a more compact porosity arrangement for the geological formations. Here is a real picture of a pore space. This is a sandstone, meaning that each particle you see here, each grain you see here is a quartz, right? It's very much like beach sands, but now they get consolidated and became a rock, basically. So this is more like a arrangement for us, okay? It's not like spheres right next to each other line, but what you see here is that things are getting compacted and sediments are getting buried, and also the shapes of these grains and their angularity versus roundness, platiness, right? And as well as the size. So now if you look at here, basically, you can easily see that here you have this pore. It looks like a cave, right? And here's another pore, right? So it seems like this pore and that pore is interconnected to each other with this channel, like we call them throats, right? So you can have similar discussions here. Here's a pore, here's another pore, and these are connected with a very small pore throat. Right? So if you like, by looking at these images, you can come up with a model, a simplified model of this rocks pore network in terms of pores and throats that connect the pores. Okay. So in that picture, then basically the pores would be the spaces available for storage of the fluids, and the throats would be the flow paths for the transmission of the fluid from one pore to the other, one pore to the other, and this way all the way to a wellbore. So it turns out that porosity is being controlled by these cave-like structures, and permeability is controlled by these throat-like, bridge-like structures, right? So if the throat gets larger, permeability goes larger. If the porosity goes larger, this indicates that actually the arrangement of grains in such a way that you have much larger pore space per bulk volume. Okay. So if you notice that also, basically these are not pure, clean grains. Over time, experience clay deposition on it. Clays here looks like sort of like snowiness, kind of dirtiness, flakiness on these grain bodies. So this is a very common feature too. I mean, these rocks are not clean all the time. There's clays and silts, much smaller bodies becoming part of the pore network and attaching to the grains and influencing the fluid's movements over time. Okay. Another thing that you can maybe point out here is like cementation. Like here, there's a one piece, here's another piece, here's another piece. You see that this is a high cemented area here. What are we talking about? Is that once grains settle, the formation water interacting with the environment solids start precipitation reactions, like calcites getting precipitated. Like we always see calcites in the pools, right? Like if you're drinking tea, you have a kettle. If you look at the bottom of the kettle, you see over time scale building. These are similar phenomena, precipitation reactions. So geological environment in the presence of groundwater could lead to precipitation reactions, and this leads to cement, right? So what is cement is that is a solid body that binds together the grains. Cementation, right? Have you ever heard of this? Cementation is very important, but basically we have it changes the porosity in a sense. It takes, because it's a new solid phase coming into picture, it takes up some of the pore space, reduces the porosity, but brings a mechanical strength to this porous material, because grains now much more stronger connected to each other mechanically. They support each other, right? So there is variation in grain size, grain shape, the cementation is changing, the clay presence, and mechanical and chemical compaction. All these phenomena are going on in sandstone, unlike the billiard balls that we looked into. So people working on these, they realize that actually they can come up with simplistic models representing the pore networks of real rocks. For example, you can have a core sample, a sample that comes from your wellbore. You can look at the pore structure of the sample using X-ray micro-CT, right? Micro-CT meaning that it's very much like a X-ray machine, like you go to the doctor to get your X-ray because you broke your hand, right? So basically, to find out where the crack is, they take an X-ray thick pictures, image of your hand, right? So here you have the same technology, but it's focused rather than targeting your hand fractured or not. It's targeting the pore space in the system. If it's micro-CT, it's even much better in terms of its focus. Actually, it can go in and detect very small pores in the system. So this is the micro-CT image of a real rock sample. You can see The blue features here, more like the lakes, on a map, right? They are the pore bodies. So if you look at the surfaces, you don't see the connectivity very well, but these pores are interconnected to each other with a certain level of connectivity, okay? And that's the key quantity, actually. We have these pores, but how well they are interconnected to each other. So a micro CT gives us ability to see things connected to each other in 3D. One way of further simplifying an image like this on the left is to create extract a pore network model out of this. So the way we do this is that it's all digital process. We identify where the pores are and where the pore throats are. So wherever the pores are, we put a sphere with the same volume associated with that pore. And once we identify the pores, we interconnect them based on their connectivity using the micro CT image. So these will be the tubes, little pipes connecting these pores. So if you do that, this pore network model of this rock based on this micro CT image would be something like this. So the blue lines here are the connectivity, the pore throats, and the red bubbles are the locations of the pores on their sides. This is what we call a digital rock. These are digital rock. On the left, we have a digital rock using micro CT. On the right, we are extracting the pore network of that digital rock in a 3D segment. Okay, so we study these not often, not a lot, but we try to do these in the early process of reservoir characterization, because we would like to find out the connectivity in these pores, which is really important for permeability identification. Once you create this, actually, you can saturate it with fluid, and you can even simulate the fluid flow in this pore, and you can measure its permeability digitally. Okay, so similarly, you can also calculate the porosity. We know the bulk volume of this pore network model. You know the dimensions of it, right? Here's A times B times height, C, ABC gives you the bulk volume. And you collect all the pores and the pore throats, add them up, that's your pore volume. So the ratio is your porosity. So porosity can be calculated. If you let the fluid flow through it in terms of simulation, flow of simulation experiments, you can predict the permeability. So this is how we use these networks. So here's another network. Basically, these are from different resources. These are basically obtained again using micro CT, then converted into pore network. So this is indicating to us that these rocks do not have huge holes, big pockets of storing fluids, units, right? A huge container. No, this is a pore network system. Your matrix, the rock matrix, has this pore structure, and we are trying to gain insight into it by looking at these visual pictures. So here on the right hand side, again, you have the spheres representing pores, and you have the rods representing the pore throats. But on the left hand side, I think there is a beautiful picture of another approach, digital approach, where actually you can see the connectivity between the pores very well. For example, here's one pore. Can you see my pointer? And this is being connected to another pore this way, and this way, and that way. It seems like it has 3 connectivity. So this is what we call coordination. So here, a pore, how many connection has? That's coordinate. Here's another pore. Now it has 4 coordination. So what is the between the 3 and 4 and 5? As the coordination number goes up, delivering the fluid from one pore to the others will be a lot easier with the coordination number getting larger, right? So here's another network, a 3D network showing actually the interconnectivity of the network. As you can see, there's not a lot of thing going on here. This part of the matrix lacks the pores and connectivity. So this is a a solid-rich region, right? But as you move to the left-hand side and look at that area emphasized with this red circle, you see significantly improved connectivity. So this is a region of highly developed connectivity, which is going to improve the fluid transport, okay? There will be more storage, and that stored fluid can be flowing a lot easier. And what needed is the pressure drop. You remember fluids flow from high pressure to low pressure. So somehow you can apply a pressure drop to this network. You will see that actually within the circle, fluid migration will be a lot easier. Typically, we give this pressure network by drilling a well and start producing. So the location of the well becomes the low pressure end, and things start flowing towards the well. Okay, so that pressure drive that you need to displace the fluids in that pore network is satisfying, is given to the system by drilling a well and start producing. So there are many images like this. I mean, here's another set, basically. You will see comparatively how a sandpack compare with Bentheimer sandstone and then a Portland carbonate. So these are ABC. On the top, you see the X-ray CT, and on the bottom, you see the pore network of the system has been calculated numerically. Clearly, the sandpack on the left has huge pore volume and that wall connection between the pores. When you go to a Bentheimer sandstone, now the porosity volume went down. What happened? Well, compaction, sedimentation, and everything that comes with geology make that sandpack more like a rock. So the rock, sandstone, lost some of its ability to store fluid and connectivity to transmit the fluid, right? This is still a good network, but not as good as a sand pack. Here we are packing a sand. You are going to a beach, you are getting a bucket of sand and you're bringing to laboratory and packing. So this has a lot of pore space, obviously. Whereas the carbonates is known to be low porosity system and it has a multi-scale pore structure. So here in this case, carbonate has a much poorer looking pore size, pore structure in terms of porosity and permeability. Here's a really interesting study. We do this kind of studies to improve production. This is what we call production enhancement, right? So we are trying to enhance production of a well by acidizing the matrix. So if your matrix has the right lithology, you can flush the matrix by pumping an acid solution into your wellbore, and the solution is going to go into the pore network wherever it finds, the right minerals that it can react, like carbonates, starts, melting it. Carbonic acid injection could lead to a new porosity and permeability development. For example, here on the left-hand side, you see the original pore structure of the rock, and we are considering matrix acidization for this rock. So we take this rock sample to the laboratory and flush it matrix acid solution and see what happens. And this is after the acid solution treatment. You flush the matrix with acid, so the injected solution went and created these wormholes, in a sense. Here, acid is actually interacting with the matrix, eating up the matrix and creating new flow paths and more porosity. So these kind of features desired during production now because it's going to enhance our production. So we do these tests in the laboratory. We have set up like this. Here we put our sample. In this case, it's a limestone. And the idea is that you basically inject acid solution. This is where the water and acid is mixed, and solution, the solution has been tuned to a right concentration of acid. And then that right concentration of acid, as part of the design, is being sent into the sample. This arrow is showing that actual direction of the flow. And then whatever comes out of it is being collected in this collected tank. Okay. So this is what we call core flooding apparatus. We use all the time in reservoir laboratories, petrophysics laboratories. You will, for sure, at least twice, you will see core flooding. In the laboratory, you are going to make measurements using core flooding. So here, the idea is to modify the existing pore structure of a limestone, which is poor, low porosity and low connectivity. So we acid flush and create new features. So these are the main components of a sandstone matrix. So we have this framework materials like quartz that creates the framework, but there is variability such as feldspars, right? Or calcites or dolomites. You know, you can have variability. These are additional grains that comes into your mixture. and then over time, these have been cemented to each other, creating a consolidated matrix with a certain porosity. Okay. So what are the factors affecting porosity? Particles or grains shape, size, and uniformity. Particles packing, whether they are randomly packed or close packed. Degree of cementation and the nature of cementation material. The stress that the rocks experience, such as overburden stress. For example, imagine your rock experiencing stress. As they go deeper, they get buried, there's more stress working on it. That's going to be a reduction in porosity. We see in formations all the time, as we go deeper, rocks getting lower porosity because they are getting compacted. And in certain occasions, like if the certain minerals experience acidic formation water, this leads to dissolution reactions and creates bugs and fractures, right? So these are like factors that increase the porosity in a sense. So this is showing the particle's shape. If it's round versus spherical body. So imagine that things are getting more sphere in the vertical direction upwards, and things are getting rounder from left to right. So here there are some images trying to represent this sphericity and roundness changing as you go from left to right and from top to bottom. Okay. So these are, for example, well-rounded samples. There's no angular features. It's really smooth and nice. But at the bottom, it's more platy, more elongated. And as it goes up, it becomes more spherical. So sphericity is increased, right? But if you go to left, now you have the same behavior, but now your sphere has more rugged surfaces, more angular features. How is the porosity being influenced by this? Well, it turns out that with increasing sphericity, porosity increases. So platy material, elongated material, they get compacted easily, so there's not much space between them. But as the things get spherical, porosity improves. And the roundness, okay? So the porosity increased the opposite way. With the increasing angularity, the grain bodies can locate themselves, controlled by angularity rather than minimum space. So that becomes an increase in porosity. So angularity is an increase in the porosity of the system. So I just show you using images, porosity increase with angularity of the particles, and as the range of particle size decrease, they also, like imagine the sizes of particles being distributed. If the range of particle size decreased, meaning that the particles getting similar sizes, then porosity will increase. And as the volume of interstitial and cementing material decrease, obviously less cement, more space. So in the presence of bugs and fractures, there's more porosity. Note that again, porosity decreases as the compaction increases. So the greater the depth generally means higher overburden stresses, higher compaction forces, and a lower porosity. And here's the grain size sorting in sandstone, actually, on the left-hand side, upper corner, you have a very well sorted material, right? So this is a highly sorted material, and the porosity is being improved in this. Compared to this one on the right-hand side, things are not very well sorted. We have very large grain bodies with respect to very small grain bodies. So this is a poorly sorted material, so that's going to be a negative impact on the porosity. Here you can see how well the grains are sorted. As the sorting quality goes up, the porosity is going up. Okay, so it's actually in a sense it's showing the particle size distribution or grain size distribution. If you have a large distribution like this one, then you have poor porosity. But if the particle size distribution is very narrow, this means that particles are all similar sizes, then you have improved porosity. This is kind of interesting slide. It's showing the porosity of carbonate rocks. Remember, carbonate rocks are also sedimentary rocks, very much like sandstone, but they are way different in terms of their pore structures. The reason is that carbonate rock is more interactive, more reactive with the formation of water compared to sandstone. Sandstone formation also experiences some diagenesis effects, but it doesn't change the porosity as much as the porosity change experienced in carbonates, right? And the reason for this, again, is the carbonates are reactive materials, right? So here you see thin section images of carbonate samples. Here on the left, I'm not sure if you've seen thin section images, but geologists create these surfaces of frozen bodies. Here, blue color is representing the pore space at that surface. So typically you can see these much more clearly under the microscope in terms of pore bodies. For example, if you look at here, you have major large pore features here. It's large blue bodies abundant here, and they are large. But if you go to further southeast corner, you see that very, very small blue pores, almost invisible. I mean, you can capture them, it's just because they are painted in blue. Otherwise, you wouldn't be able to reflect it on the scale using this image. So basically, so this is indicating to us that carbonates are multi-scale pore structure. In one sample, you can have very large pore body like vugs and fractures. Here, what we see as a large blueness is the vugs. Basically, carbonate reacting with water ended up having more and more pore space. Remember the dissolution reactions. Dissolution reactions increase the pore space and gives you the more vugs. Or it could give you fractures, like on the image on the right-hand side. You see the fracture here? That's another feature of carbonates. They are rich in fractures. These fractures develop over time due to many reasons, like tectonic activities or, geological formations going up and down due to tectonic activities. So stress fields changing because fluids moving, migrating, stress is changing could lead to fracture development. So there are different types of fluids. Different types of pores in the system. There are interparticle pores, like I show you here, pores between the particles and grains. Imagine the billiard balls images, right? So we have particles and there's spaces between the particles. This is what we call interparticle grains. And sandstone is mainly interparticle grain. But in carbonate, we also have intraparticle porosity. Intra meaning that take one of those grains, like imagine you're looking at your billiard ball, and inside the billiard ball, you start seeing pores as well. So this is the porosity in the grain. So we call it intraparticle. So there are other types of porosities too, but I don't mean to get into all of these. So what matters is interparticle, intraparticle, vugs, and fractures. And in this image, actually, you can see all of them. Perhaps you don't see intraparticle porosity. And for that, I think I have the next slide here. You can clearly see actually in this image that here is one grain. This is a carbonate. And here's another grain. And in between, there used to be another grain. You can actually trace it. I'm trying to trace the boundaries of this grain using my pointer. There used to be a grain here, but that grain has been dissolved and it starts creating its own porosity. So now it looks like a ghost grain right now in this image, but that grain has porosity in it. So what happened, how that porosity developed? Again, this is due to nature of carbonate. Carbonates being reactive, right? So the water partially dissolves the body. Here, in this case, this is a feldspar body. A feldspar body is partially dissolved and created an intra-particle porosity. Sometimes we call them secondary porosity, right? Secondary porosity meaning that grains went down and created their own pore space based on their interparticle porosity. Everything settled down, and then over time came water and created these secondary porosity features due to dissolution. Microcracks could develop, fractures could develop. This is all after the sedimentation, so we call them sometimes secondary porosity. Secondary meaning that these came in after, right, and contribute to total porosity of the system. So here's another type of rock. This is the porosity in a source rock, actually. I was talking about the source rock earlier in my previous lecture. This is a shale sample, actually. This is an unconventional rock. So it is mainly inorganic. You see the inorganic part as a light gray in the scanning electron microscopy image. This is not X-ray CT. This is not a photo thin section or something. This is a scanning electron microscopy image. You have to focus on, focus on, focus. So here you see these fractures. Actually, they are very small fractures. We call them cracks or microcracks. So they develop during the fluid generation and migration. So basically, this is sometimes we call them popcorn cracks. You know, it wasn't there to begin with when the shale formed, but then a stress field change and created these cracks. So these are what we call inorganic pores sometimes in the case of shale. But if you take a closer look at what's happening right here, if you take a look at here, you see that there's like little cute little, it's like somebody take the needles and punch holes in them. They look in black here, kind of like finely dispersed. If you take a close look at these areas, let's say you take this area and take a close look at it, you can see better actually. Now what you have here is the darker shaded regions being the organic matter. So source rocks has organic matter, and you can see this in the upper image, like the shaded areas where the dirtiness maybe, if it's the right word, I'm not sure, but you can see that here, for example. This is a organic rich region, but it's hard to see their pores unless you have a strong scanning electron microscopy. So this is a one that actually now we focus now we go to sub-micron scale. So the size of this pocket, kerosene pocket, is like 500 to 700 nanometers, which is 0.5 to 0.7 micron, right? And you look at it now, it has its own pores, and these pores are very small actually. These are about 50 to 100 nanometer pores. And if you look at closer and closer, you will see that actually down to a few nanometer pores, kerosene has pores. So these pores are part of that fluid generation process when biomass that has been buried with shale converted into petroleum fluids. The fluids created these pores, okay? Sometimes we call them kerosene pores. So here, when you make porosity measurements, you record as total porosity, the porosity associated with these microcracks and the porosity associated with the kerosene pores. So you measure the total porosity of the system, But if you ask the question, where is this porosity coming? So some of them are coming from kerosene, some of them are coming from the outside of the kerosene, the inorganic part of the matrix. So this makes the pore structure of the source rock multiscale. So there is a nanoscale organic pore network. They are at the nanoscale, and there's this micron scale inorganic pore network. So they kind of interacting with each other, adding up total porosity of the system. Okay, so in terms of connectedness, there's the issue. For example, in the previous slide, how well the organic nanopores connected with the microcracks and fracture at the large scale, right? Are all these pores connected to each other? I don't know, maybe, but there are methods that allows us to measure the so-called effective porosity associated with the interconnected pore body, and there are methods that measure the total porosity. Okay, so total or absolute porosity, let's define it as Pht. That's the total pore volume divided by bulk volume. And we can also measure effective porosity, which is including the interconnected pores only. Then we measure Phe. This is the interconnected pore volume divided by the bulk volume. Okay, so very clean sandstones, they have total porosity close to effective porosity. Poorly to moderately well-cemented intergranular bodies, they have total porosity almost same as effective porosity, but highly cemented materials, most carbonates, and some of these source rocks with multiscale pore structures have effective porosity that could be less than total porosity. So we need to be careful what we are measuring. So I'm going to go over the definition of saturation, and I'm going to stop. I think we have enough recording for today. We have about 42 minutes recording so far. So what is the fluid saturations? So typically this pore network that we have been talking about is actually holding up multiple phases of fluids like oil and water, oil and gas, oil, gas, water. So each phase has its own body taking up certain portion of the pore volume, right? For example, here on the left, you have the pore body that has been created. It's empty. So you see in white color is the total porosity of the system. But typically, this is not empty. I mean, there is no emptiness in the formation. There's always something filled in it, right? So it's typically, it's saturated with oil and water for a petroleum reservoir. So if you look at that space, actually, you see that water, which is shown in here in the blue, taking up the space, that pore volume, by the grain surfaces. So some of the pore volume is taken up by the water, which prefers to be next to the grains. This is due to the fact that grains are warm wet rocks. In this case, if the grains have affinity to water, water creates some sort of a film, but still taking up some of the space. And oil takes up the central portion of the space, right? So basically now this whole pore volume is taken by oil and water. How much is taken by oil? How much is taken by water? That's the saturations. So we say water saturation is equal to the volume of that water in that pore network divided by the total pore volume. Okay. Similarly, oil saturation will be the volume of oil divided by the total pore volume. So these are fractional values. So in this picture, it's just water and oil. So if you take the saturation of water and add up to saturation of oil, it should add up to 1.00000 because there's nothing else. All of the pore space taken by either water or oil. So the saturation should add up to 1. Here's another case. Now imagine that, for example, the pressure of the system is getting depleted. Now at one point, we reach to pressures below the bubble point pressure of the oil, so the gas bubbles starts coming out of it. Now, what we have additionally is gas bubbles. Here you see them in terms of light color, the yellow color. So still we have water volume by the grains, oil volume by the central portion of it, and gas volumes appearing, evolving, coming out of the oil phase. It has its own phase. So of course now the gas saturation comes in as an additional value. Here, gas saturation would be the volume of gas divided by the total volume, right? If you add them up total, we have water saturation plus oil saturation plus gas saturation equal to 1.000. I'm going to continue with another recorded video to these slides, but at a later time. So I'll stop here. Okay, I'll see you later. Hopefully, I'll see you all on Tuesday in the classroom at 10 a.m. All right, bye bye.